May I also ask a question
Sure.
later, maybe?
Okay, sure. Okay, so let me do a quick screen share. Uh, so the issue that we're working out right now is um, the fact that we've got at this line right here, we've got two copies of the context that is typed A. And that's because if you look at the rule up here, the Z is duplicated here. And now the interesting point is that at least with respect to the typing, um, the typing doesn't care if this is a Z and a Z prime because they're both typed A. So it doesn't care. Certainly, if it holds for a Z and a Z prime, then it would hold if it were two copies of Z. Is the observation. However, it messes about with the getting rid of the right here. We have a problem if we keep a careful account. We have a problem because the if you're taking the whole from the sort of the head of the list, which is running this way, then we can't discharge these rules here. So we want to be able to um, discharge the both copies of the A on the left hand side. When we do this rule here, um, that's the real issue, or that's the sort of the nub of the issue in this proof. And so there is a way to do that, which is rather than to treat this as a list, we treat it as a type environment. So it's a mapping, and then these are given the holes are given names. So it looks like we are, at least in order to get these results out the door, because there are so many of them, rather than block them on sort of a stubborn pursuit of linearity for the use of the context hole, we will switch over to second order algebraic theories. So that's, let's see if I can find that here. Hang on a second. Let me stop screen sharing while I try to find this paper. Here it is right here. Okay,
So,
go ahead.
are you saying that because they're the same type, you can treat it as only one whole instead
Uh,
of two?
it's not just, it's not because they're the same type, it's because in the rewrite rule, it's actually the same resource. So let me go back to screen
Okay.
share and show you what I'm saying. Okay, so here's the rewrite rule, right? And this Z is actually duplicated. So when we do the bookkeeping here, we need to account for the fact that that Z is duplicated, and which would be fine if we had names here. If we had X was typed this way, and Z was typed A, and Y was typed A to B. Then
So we need to track how many times this resource is used, right?
um, Well, again, if it's type environment, we don't have to track the number. We're free to copy it as many times as we want. It's just a
Okay.
mapping from a name to a type. So what we'll do is we're going to take essentially the ideas laid out in this paper. So I can show you the syntax. So they have a two-level type environment, right? So they have type assertions here and then meta assertions here. So meta variables, which allows us to get binders, right? So the meta variables are allowing for us to have a binder syntax together with a capture avoiding substitution. So here's an example of the lambda calculus. So you would have a term, an operator called application and an operator called abstraction. And then these things here are meta variables. Note that M is given an arity, which is that it's a context. Now this is a simplification because you need to be able to make substitutions even when N is an abstraction. But this says that right now N is a closed term, so you would have you'd have the ability to do substitution. The way capture avoiding substitution happens is done by the structural induction here. So the basic idea is if you have that theta get together with, I don't know how to pronounce this yet. I haven't got a good way of pronouncing these kinds of type judgments. But essentially, theta together with the x1 through n gives you t, and theta together with gamma gives you ti. Then you can substitute the ti's for the xi's in t according to these rules. So if you've got an xj, then ti for xi is going to be tj, right? That's just natural. If you, for any of the terms in here, if you apply the substitution, you're applying the substitution, you're pushing the substitution in. When you've got binding, then you do essentially fresh Z, and then you do the substitutions of the TIs for the XIs and the ZJs for the YJs. So that gives you the capture avoidance. And then there's a notion of meta substitution, which basically just pushes everything through. So then you have a notion of equations, and so for example, this is there's your beta reduction, and there's eta, right, which basically says that this is extensionality, right? So the abstraction, it's basically lambda x f applied to x is just going to be the same as f. So that's extensionality, which we were using heavily over in this proof over here. And this is beta reduction. So we will use this machinery. This is the syntactic machinery, and then there's a corresponding categorical interpretation. that lines up with the way algebra is typically interpreted from a categorical perspective, which is how we're treating our rewrite theories, right? So it's a relatively good fit. And doing this allows us to also have a nominal solution, right? So it kind of picks out a nominal solution that will allow us to treat a larger class of theories than the combinator theories we've been applying lately. So that's essentially the work that Mike and Christian and I have been focused on in order to clean up the system a little bit and make sure that we don't have any issues with duplication of proofs. Duplication of resources and proofs. Does that make sense?
Yeah. Is this related to higher order abstract syntax?
Yes, that's exactly what this is. Yeah.
Oh, okay.
Yeah, that's it. Okay, so that's kind of our research. I did want to mention something else, just for fun. I strongly recommend that if people are interested in sort of the query side of Rolang, to look at Abramsky's interpretations of the process algebras, as opposed to the process calculi, the process algebras as relations extended in time. So it was Codd who was the one who sort of promoted the idea of relational algebra for queries. And Abramsky basically said, well, look, you can take the tuples of a relation. So a relation is basically just some subset. A relation on X and Y is just some subset of X cross Y. Another way of saying it is that it's an element of the power set of X cross Y. So you could imagine doing a recursive domain equation. You can think of it as a data type, where it's where P of XY is going to be equal to the power set of X cross Y cross P of XY. So you can think about expanding, you can think about that as expanding your ordered pairs in the relation to ordered triples, where upon checking the relatedness of, say, little x to little y, you now get a new relation. So every time you check relatedness, that observation leads you to an evolution of the relation. So you can think of that as closely connected to input meets output, and you get a continuation. So that's kind of the very, very similar notion. So that's useful for checking, for kind of beginning to understand how Rolang is connected to query semantics. But I've been talking a lot about geometries and process algebras. And one way you can think about the motivation for that sort of investigation is that it was really the Einstein program of interpreting gravity as an evolution of the metric. Right, so as matter and energy moves around, the distribution of matter and energy changes in the space, in the manifold, then you get a corresponding shift in the metric because space is warping. So that's kind of the intuitive picture of Einstein's geometric interpretation of gravity. Um, so so essentially, that's giving you geometries that evolve in time. Well, if you look at the Erlangen program, which was uh, generalized by Cartan um, to kind of capture more geometries and better fit the Einstein uh, sort of intuitions and utility. Groups and certain symmetries are what give you um, they give you the geometry. So one way to think about geometry in this is in terms of Abramsky's idea of relations extended in time. So you could think about symmetries extended in time. So so this is very again, you can think about this in a kind of operational sense. Groups capture a notion of symmetry, and it is a remarkable fact that do and undo is all you need to capture some notion of symmetry. So in particular, so what do I mean by that? Well, so the group operation comes with this notion of an inverse, right? So the fact that every element of the group has an inverse is essentially what is necessary to capture this notion of symmetry. And so you can, in the same way that you can think about extending relations in time, you could imagine that the characterization of the group operation is one in which you look at the you look at the group operation as giving you a continuation. So after you've taken A and B and you've calculated the result of the group operation, you don't just get the result, you get the result plus a continuation, which is the new group, which may represent a new symmetry. So if you get symmetries evolving in time, or symmetries extended in time, then that should correspond to geometries extended in time. So that's another way of relating the process algebraic intuitions to the geometric ones, which I think might be helpful for classical mathematicians who have been thinking about this from a different perspective and have not been thinking about the process algebras as invariants that capture particular kinds of information. So hopefully that made sense to folks.
Yeah. So you said you get you return new group which can contain new symmetries.
That's right. Well, you return. So you know, like, let's say the group operation is star. So A star B returns C together with the next group.
And how we relate properties of this next group to existing one? We introduce these new symmetries.
Yeah, you probably want some notion of continuity, right? So some kind of computational continuity, right? So that's the interesting bit.
So we are introducing some new constructs in this way, right?
No, they're not necessarily syntactic constructs, right? It's you're I mean, you know, the lambda calculus doesn't say anything about continuity, right? It just gives you beta reduction and alpha equivalent. But it turns out that the continuous functions on you know, on the lambda domains are the ones that model the terms in the lambda calculus. So computation is already closely connected to continuity.
I see.
Yeah. So you had a question you wanted to ask.
I mean, it's not related to this directly. It's related to Univalis principle that you mentioned, and also I mean, I'm interested. You mentioned in lectures design of introduction to design of computational calculus. You mentioned full abstraction.
Oh yes.
And so I was trying to connect these things, and also you were talking about biosimulation. So what is the connection between these things?
Yes. Well, in general, univalence principle is trying to capture is trying to say something about what does it mean for two things to be equal, right? To abstract that a little bit. And biosimulation also abstracts what it means for two things to be equal. And full abstraction is yet another notion of equality. So they're all related in that sense. They're all talking about equality. Biosimulation says, again, a sort of equality extended in time. So P and Q are bisimilar to each other if anything P can do, Q can do, and vice versa. And whenever you get to a new state from something that P can do and Q can do, then the two new states, say P prime and Q prime, are also bisimilar to each other. So it's pretty clearly sort of equality extended in time, and full abstraction uses notions of equality to build up a larger sense of equality, right? So two models of computation, or let me say, an interpretation of a given model of computation is fully abstract if whenever P is equivalent in the notion of computation we're investigating, say the lambda calculus or the row calculus, whatever, whenever P is equivalent to Q, then that means that the interpretation of P is equivalent to the interpretation of Q, and vice versa. Whenever we have that the interpretation of P is equivalent to the interpretation of Q, then we get that P is equivalent to Q. So that's saying essentially that the syntax and the semantics have the tightest possible fit. So you could, another way of saying it is that, you know, the semantics is just another syntax, or that the syntax is another way of viewing the semantics. So those are all sort of the same idea in a fully abstract setting. Does that make sense?
Yeah. So they're not the same. There's like you said that in the lectures you said that full abstraction is parametric in the two different forms of behavioral equivalence.
That's correct. That's exactly right.
So with biosimulation, we are using some specific notion of full abstraction. Is this
no, but biosimulation is a notion of equivalence. It's
okay.
Right. So you can talk about, you know, full abstraction for a process algebraic setting that uses biosimulation.
Okay, thanks.
Sure. Absolutely.
I was also watching Philip Wadler's talk about Pluto score and smart contracts, and he was mentioning also full abstraction, and I'm not sure if he means completely the same thing, but
well, I'm almost certain that he does. We can, if we we can go look at what he's talking about and probably identify that.
So I can share a link when I
Put it in
when I
Discord.
wrote some.
Put it in
Yeah, sure.
Discord. I'll take a look at it. I'm gonna jump off here at the half-hour mark because I've got to take care of something before stand up. But thanks to all for this this session, and looking forward to next week and see some of you in Dev Stand Up in just about 30 minutes.
See you. Thanks.
Yeah, thank you, Greg. Appreciate it.
Yeah, sure. Ciao for now.